Now, welcome to electrical machine lecture. Now we will continue with the previous topic, that is the speed control of DC motor. We have seen the speed control of DC motor by two methods. One is the armature control method. This method is applicable to control the speed below normal value of the speed. And second is the field control method or flux control method. This method is useful for uh, speed control above normal value. Now, today we will solve some of the numericals. A 230 volt DC shunt motor runs at 800 RPM and takes armature current of 50 ampere. Find the resistance to be added to the field circuit to increase the speed to 1000 RPM at an armature current of 80 ampere. Assume the flux proportional to the field current. Armature resistance is 0.15 ohm and field resistance 250 ohm respectively. So here the some data is given. Here the voltage of motor supply voltage V is equal to 230 volt, whereas the motor speed in the initial condition N1 is equal to 800 RPM, whereas in the second case the speed uh, we want to increase the speed up to the 1000 RPM. So here the speed is going to increase. So this increase in speed is done with the help of resistance to be inserted in series with the shunt field winding. That is the field control method. So this is the armature. Initially, the speed of motor is 800 RPM. Therefore, to improve the speed from 800 to 1000 RPM, we have to put the resistance in series with the shunt field winding. Then and then it is possible to obtain a speed more than the rated value or the first condition or initial condition. So this is the voltage V, current I, armature current IA, and shunt field current ISH. And this is the RSH, shunt field resistance, armature resistance. So the value of armature current taken by motor is I1 is equal to I1, which current added to the, okay, which takes the armature current. It's not a total current, it's the armature current I1 is equal to 50 ampere. In second case IA2 is equal to 80 ampere. Whereas armature resistance is given as 0.15 ohm and shunt field resistance RSH is equal to 250 ohms. Okay, so we can calculate very quickly the shunt field current ISH is equal to 230. Shunt field current is equal to 230 divided by RSH plus R. Some external resistance R is connected in the second case. So this is the case 2 when the external resistance is connected. Whereas in the case 1, ISH1 is equal to 230 rated voltage divided by 250. 230 divided by 250. So it is 0.92 ampere. Okay. So initially there is no resistance in series with the field winding. Therefore, the motor is going to run at the speed N1. When shunt field winding is connected with the external resistance R, the current is going to decrease. That decrease in current in the field winding decreases the flux, and we know that the speed is inversely proportional to flux or field current. Therefore, the speed of motor increases from 800 rpm to 1000 rpm. Now, first calculate the back EMF in the first case. EB1 is equal to V minus IA1RA, which is equal to 230 minus 50 into 0.15 equals to. So it is 222.5 volt. Whereas EB2 is equal to V minus IA2RA. It is 230 minus 80 is the armature current. 0.15 equals to 218 volt. So we know the relation, or the N2 upon N1 is equal to EB2 upon EB1 multiplied by, as the speed is inversely proportional to, so it is ISH1 upon ISH2. So we don't know the value of ISH. So it is possible to calculate the value of ISH. So here the ISH we can calculate from this all these values, that is N2 is equal to 1000 rpm divided by 800 rpm equals to EB2 is 218 divided by 20 222.5 into ISH1. We know the value of ISH1 already we have calculated. So it is 0.92 divided by ISH2. So in this case, what is the ISH2? It is the 230 divided by this one. So if you put the value as 1000 divided by 800, 218 divided by 222.5 into 0.92 divided by the total resistance. Let we assume that let RSH plus R, external resistance, is total resistance RT. So it is equal to 230 divided by RT. Therefore, RT is equal to, total resistance is equal to 309 ohms. As shunt field resistance RSH is equal to 250 ohm, 250 ohm. Therefore, the external resistance R is equal to 319 minus 250 equals to 69 ohms. So this is the resistance to be added in series with the shunt field winding to obtain the required speed. So the resistance, the external resistance 69 ohm is to be connected in field circuit in field circuit to obtain speed 1000 RPM. Now from this one, we can calculate the ISH2. So ISH2 is 230 is the supply voltage 319. So definitely ISH2 must be smaller than the field current in the initial condition. So it is equal to 0.721 ampere. It is smaller than the 0.92 ampere. Now the second numerical, a 220 volt DC shunt motor with armature resistance of 0.5 ohm runs at 600 RPM on full load and takes armature current of 20 ampere. If the resistance of 0.1 ohm is placed in the armature circuit, find speed, full load find speed at full load torque and half full load torque. So in this case, what points are given? It is clear that a motor, when a resistance, if the resistance of point is the resistance of 1 ohm is placed in the armature circuit, means we are putting the external resistance in series with the armature circuit. So it is a armature control method. And when there is a armature control method, the speed is going to reduce from its initial value. So it means that the new speed uh, uh, which is going to be calculated is definitely less than the 600 RPM. Okay, so for that purpose, the given data is N1 is equal to 600 RPM, whereas back EMF we can calculate is the when armature current IA1 is equal to 20 ampere and armature resistance RA is the 0.5 ohm and external resistance R is 1 ohm, isn't it? So the back EMF EB is equal to 250 minus IA1, that is 20 into 0.5 equals to 240 volt. Since the torque is directly proportional to current and armature flux, sorry, shunt field flux. So torque is directly proportional to flux into armature current. We can say that TA1, TA1 or TA2 upon TA1 is equal to IA2 upon IA1. Since the torque is find the speed at full load torque, let the torque is not going to change in the first case. Here the torque for full load condition we are considering the torque is same. So under such condition we can say that pull load condition, TA1 is equal to TA2. Both are same. So IA1 is equal to IA2, which is equal to 20 ampere. So now EB2 is equal to 250 minus 20 into a resistance is added, your RA plus some resistance R, which is equal to 250 minus 20 into armature resistance is 0.5 plus 1 equals to 220 volt. So now what is the speed? Now N2 upon N1 is equal to EB2 upon EB1 into phi 1 upon phi 2, since current in shunt field winding or circuit is constant, we are not inserting any type of resistance, external resistance. That's why N2 is equal to, okay, that is phi 1 is equal to phi 2. So N2 is equal to 600 multiplied by 220 divided by 240. Therefore, speed N2 is equal to 550 RPM. So this is the initial value, that is the at full load condition or rated condition. This is the speed. Now, the second part says that the torque is half to the first condition or the previous condition. So we consider that in the previous condition, the armature current is 20 ampere. Okay. So now we will take the second condition as a initial condition. So TA2 upon TA1 is equal to IA2 upon IA1. Since torque is directly proportional to armature current, since it is a shunt field motor, and in the case there is no external resistance is added in the field circuit, we have added the resistance in the armature circuit. Say the shunt field winding is as it is, there is no increase and decrease the field current, so the fluxes are called constant, whereas a resistance is added whose value is 1 ohm in series with the armature circuit. In the armature circuit, we have added the external resistance, and that resistance is Ra. Armature resistance is Ra. So here torque T2 is equal to half of the torque TA1. It is given in data. Okay. So therefore, the current IA2, if we put the value, TA1 is equal to half of this one. So IA2 will be the 10 ampere, isn't it? By putting this value. So, okay, we'll put it is 1 upon 2 TA1 upon TA1 is equal to IA1 upon IA2. Therefore, IA2 is equal to uh, IA2 is equal to IA1 upon 2. So this is 10 ampere. So now the new value of back EMF we write as a EB2. So it is 250 minus 10 into 0.5 equals to 235 volt. Now put the values. N2 upon N1 is equal to EB2 upon EB1. So here N2 is equal to the 600 is the N1 multiplied by EB2 is 235 divided by 240. So the speed will be 587 RPM. So when the torque is half, definitely the speed drop will be smaller or the speed change will be smaller. And when the load on the motor will be more, the speed variation will be higher one. Third example, the speed of 50 HP 37.3 kilowatt series motor working on 500 volt is 750 RPM. There is a series motor. So we will draw the series motor. A series motor. Few number of turns in the series field winding. Since the series field winding resistance is smaller, so this is the series field motor. Now what is the point here given? It is a 50 HP. It's working at 500 volt and runs at speed N1 is equal to 750 RPM at full load and efficiency is equal to 90% if the load torque is made 300 Newton meter. So the torque in the first case TA1 is or torque is 350 Newton meter and 5 ohm resistance is connected in series with the machine or motor. Calculate the speed at which the machine will run. Let armature resistance and shunt field resistance is 0.5 ohm. So here RA plus RSE is equal to 0.5 and external resistance R is connected is equal to 5 ohm in the second case and efficiency is given. So it is necessary to calculate the current in the first case IA1. Now in the second case we will calculate the current IA2 when armature resistance when the resistance is connected in series with the motor. Okay, so the torque we know that torque is equal to 9.55 into power output divided by speed. Okay, so now the speed is given, so we can calculate the power. 9.55 into power output of the motor divided by speed 750 is the RPM, and armature torque is made equal to 350 Newton meter. So from this one, the power output is equal to, say, P out equals to, or it is given something. So output is equal to, okay, what is given? The speed of 50 HP. Okay, so here the output power is given, rated power is given. So we will calculate from the output of motor, and efficiency is given. Okay, so power output is at rated condition, P out is equal to 37.3 kilowatt. Okay, so it is equal to 37.3 into 10 raised to 3 watt. So now if you know the output, we can calculate the torque. So torque is equal to 9.55 into P out upon speed. So everything is given, 9.55 into 37.3 into 10 raised to 3 divided by 750 RPM. So it is equal to 474.6 Newton meter. So torque at full load is going to find out. Now as motor input which is equal to motor output divided by efficiency. So it is equal to 37.3 into 10 raised to 3 divided by the efficiency is 0.9, 90%. So here it is a 0.9. Therefore, armature current IA1 is equal to this power output divided by voltage. So 500 is the voltage. So it is 37.3 into 10 raised to 3 divided by 0.9 into 1 by 500. So armature current equals to 82.9 Newton, S ampere. This is the armature current. Now the torque is for the series motor. For series motor, torque is directly proportional to flux into armature current. As the flux is directly proportional to the armature current, since in case of series motor, armature current and series field current is same. It is connected in series. So torque is directly proportional to square of current. Now it is a square of current, so we can write as IA2 upon IA1 is equal to TA2 upon TA1, and this is the square relation. So this is the condition. Now if we put the torque values, we can find the armature current IA2 equals to, it is 82.9 under root 250 upon 474.6. So the current is 60.2 ampere IA2. Once we know the value of IA2, we can calculate the back EMF EB1, and it is equal to 458.5 volt, and EB2 by calculating it is 100, and so we can write as a 500 minus 60.2 into bracket a 5 ohm resistance is added, so it is a 0.5 plus 5, whereas for this one EB2, so it is equal to 168.9 volt. So we will elaborate this equation. So here EB2 EB1 is equal to 500 minus 82.9 into 0.5, only 0.5, and here the resistance is added, so it is equal to 458.5 volt. So now we come to know the value of back EMF, we know the current, so finally we can find the speed. N2 upon N1 is equal to EB2 upon EB1 into IA1 upon IA2. Therefore, speed N2 is equal to 381 RPM. So even before calculating the final value, it is possible to give the answer. The value of answer, the value of speed may be different, but as per the concept, we should know this is two. It is, the correction is there. It is a 250. It is a 250. Okay. So when we are connecting the resistance, definitely it is just like a armature control method, and in the armature control method speed is going to reduce. So initial speed is 750 rpm. While connecting any resistance or any value of the resistance in series with the armature, the new value of speed will be definitely less than the 750 rpm or the initial value. So we come to know that from the concept is that the speed will be smaller, and by calculation, if we found that the speed is more than the initial value, it means that there is some mistake has been uh, uh, done somewhere in the calculation. So these are the some few of the numericals. In the next lecture, we will again do some numerical based on both method, that is the armature control method and field control method. Thank you.